Hello students. Quantum mechanical model of atom. As per quantum mechanical model of atom, atoms contain first of all main shells. Main shells contain subshells. These subshells will be in different orientations. Simple. It is as simple as that. So, but we have to know in every main shell how many subshells will be there, and for every subshell how many orientations will be there. Right? Every orientation is called an orbital. It's very simple. What is an orbital? That we define finally, right? So now main shells. Main shells are indicated by K, L, M, N, or else N is equal to 1, 2, 3, 4. Main shells are actually represented by principal quantum number. Principal quantum number gives information about main shells inside the atom, right? As the shell number are KLMN, as you go to KLMN, shell size increases, also energy of the shell also increases. That is what first of all principal quantum number. Nothing but principal quantum number gives information about main shells. In main shells there will be subshells, right? Now in every main shell how many subshells will be there? In n is equal to 1, K main shell there will be only one subshell, and that subshell is represented by S, and subshell symbol is L, right? So this is called angular quantum number, right? So represented by small l. So one subshell in K main shell. N is equal to 1, one subshell. N is equal to 2, two subshells. N is equal to 3, three subshells. N is equal to 4, four subshells. Means in fourth main shell there will be four subshells. Now for every subshell name is required. That is why otherwise we cannot differentiate them, right? Or else, so nothing but everyone will have name in that. Similarly for our subshells also there are names, right? So in case main shell there is only one subshell, L is equal to 0 with symbol small s, right? In second main shell there are two subshells, right? One is S, other one is P, small letters, right? So they are numbered. For S subshell L is equal to 0, for P subshell L is equal to 1, right? So now third main shell. In third main shell three subshells, their names are S, P, D. So for S subshell angular quantum number is 0, 1, for P subshell 1, and for D subshell 2, right? So here in fourth main shell there are four subshells S, P, D, F. Their numbers are 0, 1, 2, 3 respectively, right? So this you have to remember. Now you have to remember one rule you have to remember. What is that? So if it is 4, number up to 3 starts with 0 up to 3. If it is 3, starts with 0, ended at 2. If it is 2, starts with 0, ended subshell numbers, right? Ended. So if it is 1, 1 minus 0, right? 1 less. Not 1 minus 0, 1 less, right? So it is 0. That is what? N minus 1. So in a main shell n, there will be totally n subshells, 0 to n minus 1. That is your remember. So what you write about subshells? So a main shell n contains totally n subshells. They are numbered from 0 to n minus 1. Right? So angular quantum number gives information about subshells and their shapes. S subshell will be in spherical shape, P subshell will be in dumbbell shape, D subshell will be in double dumbbell shape, and F subshell will be in complex shape, right? Third one is orientation. Subshells will be in different orientations. Orientation nothing but like this, X or X in X direction, like Y direction, and X, Y, Z, Y, Z direction. So you can consider on planes. These are all orientations only. These orientations which are right direction. So they will be in different orientations. What will be in different orientations? Subshells will be in different orientations. Now you have to know for each subshell how many orientations. So you know already subshells are represented by L. For each subshell L, there will be totally orientations from minus L to plus L. So where minus L to plus L, including 0, right? So totally, if you count from minus L to plus L including 0, how many will they come? They will be totally 2L plus 1 orientations will be the count. Count will be 2L plus 1 orientations will be there. So for S is equal to, for S, L is equal to 0. For S subshell, there will be one orientation. And L is equal to 0, you substitute here. Minus 0 to plus 0. Including 0. Nothing but only 1 0 only. So 2L plus 1. 2 into 0 plus 1. So totally 1. Only for S subshell, there will be only one orientation. Is it clear? Now next for P subshell. For P subshell, L value is 1. So that is why L value is 1. So minus L, minus 1 to plus 1. So minus 1, 0, 1. Totally 3. 2 into 1 plus 1 is 2 plus 1 is 3. So there will be 3 orientations for P subshell. They are from minus 1 to 1 including 0. Minus 1, 0, 1. They are also numbered, named as Px, Py, Pz. Why we have written 2 here is, it is a, the now Px, Py, Pz are orientations of subshell P, and these are in the second main shell. That is what 2Px, 2Py, 2Pz. Next, again, here let us discuss once again. So this is again same. P subshell, 3 orientations, 2 into P subshell. L value for P subshell is 1, P into 1 plus 1. So 2 into 1 plus 1 is totally 3 orientations for P subshell, and they are from minus 1 to plus 1 including 0. Minus 1, 0, 1. Right? So minus 1, 0, 1. Same here also same. Their orientation numbers, magnetic quantum number values for P subshell, whether they are in second main shell or third main shell, they will be minus 1, 0, 1 only. But we write it here 3Px, 3Py, 3Pz. Means 3 stands for third main shell. Px, Py, Pz are orientations of P subshell. Is it clear? Right? Similarly, 4Px, 4Py, 4Pz also have their respective definitions, right? Means they are P orientations of P subshell in a fourth main shell. 4Px, 4Py, 4Pz means. Now D subshell. For D subshell, angular quantum number is 2. L value is 2. So nothing but now minus 2 to plus 2. Minus 2, minus 1, 0, plus 1, plus 2. Totally how many will be? 5 will be, right? So that is why 2 into 1 plus 1 also 5. Right? Sorry, 2 into 2 plus 1. 2 is 4, 4 plus 1, 5. So there will be 5 orientations for d orbitals. You search in Google the orientations of d orbitals. Just you type what I said. Orientations of d orbitals. You will get different photos. Photos. So you see, you will find that on planes you will find 3 orbitals. Sorry, double dumbbell, no? So they will be in planes between the axes. Like this, right? If you consider this as xy plane, xy, so they will be between the axes, right? They will be between the axes. Is it clear? So that is why they are called 3R xy, yz, zx, right? Quantum mechanical model of atom says electrons are found at some different places around the nucleus. Means at those places the chance of finding electrons is more. Those places are called, those regions are called orbitals. So how do you define orbitals? The region of space around the nucleus where the chance of finding an electron is more. That is called an orbital, right? Now again, in an orbital, now how many electrons can be there? In an orbital there will be place for only 2 electrons, right? There is place for only 2 electrons, and one will be rotating clockwise, another will be rotating in the anti-clockwise. You think now, right? There are only 2 spins, that is called spin quantum number. In an orbital there will be place for only 2 electrons. There is place for only 2 electrons because one electrons will have only 2 spins, right? So one will be clockwise, another one will be anti-clockwise. One is represented as minus half, another one is represented as plus half. So as there are only two spins in an orbital, there will be place for only two electrons. Three cannot be, because if you keep three electrons in one orbital, any two electrons you must have two spins also must say, right? So that is why in an orbital there is place for only two electrons. 2px, 2py, 2pz are orbitals of subshell P belonging to second main shell. They all have same energy, right? 3px, 3py, 3pz. They are orbitals of P subshell in the third main shell. These three also will have same energy, and these three won't have same amount of energy. These three will have same energy, these three also will have same energy, but energy of these three and these three is not same. That is why, so they are called degenerated orbitals, right? What are degenerate orbitals? Orbitals of a subshell belonging to a particular main shell. Orbitals of a subshell belonging to a particular main shell are called degenerated orbitals. Is it clear? So this is what ending of your quantum mechanical model of atom. Thanks for watching. If you understand it, if you like it, you please help your friends, so that they will also learn it well.